Greetings, AP Chemistry students. I want to go over a few things with you today. The first I want to discuss, just to make sure that we're clear on this, uh, ions that are considered neutral are the ones that are the conjugates of a strong acid or a strong base because they would be weaker than water. So, for instance, our group one and group two ions that would include things like sodium, calcium, strontium, potassium. All of those ions are neutral because they are the conjugate base, the conjugate acid of a strong base. And so they would have a Ka that's less than the K of water, which means that they are less capable of producing hydrogen ions in solution than water is. And so water would inhibit them from acting as an acid. Similarly, these five anions are considered to be neutral because they are the conjugate bases of a strong acid, and therefore they can't really produce hydroxides in the presence of water. You'll notice it includes the halogens except for fluorine because hydrofluoric acid is a weak acid. And it does not include sulfate because keep in mind, sulfuric acid is a polyprotic acid and the HSO4 minus ion is a weak acid. So sulfate would be a basic salt. Next, I want to kind of finish up the notes real quick for this unit. Polyprotic acids are the ones that can produce more than one H plus in solution. And for each hydrogen ion, you will get one equivalence point. And the same amount of base is required to reach each of those equivalence points. So if we had a triprotic acid that we were titrating, however much volume is required to reach the first equivalence point, you'll require twice that volume to reach the second equivalence point and three times to reach the third equivalence point. So basically, they are spaced evenly apart. So if it took 12 milliliters to get here, the second equivalence point would occur at 24 and the third at 36 milliliters. Also, because a triprotic acid would have three Kas, you could go to right here and find the pKa1. Right here, you would find the pKa2. And up here, you would find the pKa3. So a little bit high on that. Right here, yeah, pKa3. So that's a little bit with polyprotic acids. Now, for a titration of a monoprotic acid with a monobasic base, one that produces one hydroxide and one hydrogen ion, the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base because they react in a 1-to-1 ratio. So if we look at this titration curve, let's say that we were working with uh, 0.30 molar potassium hydroxide. And let's say that we had, 10 milliliters of weak acid. Well, the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. So we could say the molarity of the acid we don't know, but that would be times, well, the equivalence point took place at 20 milliliters. Oh, hold on a second. The molarity of the acid times we use 10 milliliters of that equals the molarity of the base times, well, the equivalence point took place at 20 milliliters, so we used 20 milliliters. So the molarity of the acid would be 0.60 molar. So this is how you could actually find the molarity of an acid or base using a titration. Also, I do want to point out one more feature here, that if the equivalence point took place at 20 milliliters, then at 10 milliliters, right there, our pH would equal the pKa. Now, at that point, the ratio of weak acid to conjugate base are equal. If you are on this side of the line, if you're on that side of the halfway point, you have more of your weak acid, your hypothetical acid. And if you're on this side, you have more of your conjugate base. One thing that came up in class that I want to clarify is that HA is a hypothetical acid and its conjugate base is A minus. You could also have a weak base, which would be represented with the letter B, and its conjugate acid would be HB plus, because remember, a conjugate acid base pair differs by an H plus. So hope that clarifies a little bit. Now, the last thing I want to address is indicators. Indicators are weak acids that have a different color in their conjugate base form from their conjugate acid form, because the addition or removal of a hydrogen ion causes a change in the structure of the molecule, which affects how it reflects visible light or absorbs visible light. The color change occurs within 1 pH unit of the pKa of that weak acid. So, whatever the pKa is of that indicator, that's when it changes color. So, when you are trying to choose an indicator for a titration, you want it to have a pKa that is close to the pH at the equivalence point. So, if you're titrating a strong acid with a strong base, you want something that has a pKa close to 7. If you're titrating a weak acid with a strong base, your pH at your equivalence point will be basic, so you would pick something that has a higher pKa. If you're titrating a weak base with a strong acid, you'd pick something that has a lower pKa. There's a chart on the next slide that I'll show you. And phenolphthalein has a pKa of 9. You might think that's problematic, but when you're titrating a strong acid with a strong base, if it changes at a pH of around 9 up here is when it turns pink. That curve rises very, very, very sharply when you're titrating a strong acid and a strong base. So you'll go from a pH of 7 to a pH of 10 with the addition of just one drop of base. The pH just skyrockets up, as you can see from your own titration curves. So phenolphthalein is perfectly acceptable to use. So here is that chart that I referenced. It's on the last slide of the PowerPoint. It shows the different color changes. Phenolphthalein, it goes from colorless to pink as you go towards a pH of 9. Now, what's interesting, and it doesn't show it on this graph, is that as you go to a pH of 14, it actually turns colorless again, because phenolphthalein is a diprotic acid, and you can lose the second hydrogen and it turns clear. Thymolphthalein goes from clear to blue over a similar pH range. The reason that these are the most commonly used indicators is because it's pretty unmistakable when something goes from clear to having a color, as opposed to bromothiamyl blue, which goes from yellow to yellowish green to greenish blue to bluish green to, or whichever way that order goes. I'm not a color expert, to blue. So it's like, well, when did the color actually change? It's a little bit more ambiguous if you're trying to do a titration. Cresol red, it goes from red to yellow down here, and then it goes from yellow back to red again. These are just some examples of indicators that could be used.